Okay, good morning, everybody, and welcome to our class. On Monday, we did 2 exercises discussing the Chapter 3 problems, the first few Chapter 3 problems, energy conservation law, and we applied this energy conservation law to 2 different examples. Today, I would like to move on, and I will change to the script. Oh, sorry, you're not yet seeing it. So just a second. There it is. Okay, and today I want to talk about power and efficiency. First of all, we will discuss some theory, and then we will have a look at a few exercises, 1 or 2, see how far we get. Okay, so power, the symbol of the power is P. The unit is the W, and so power is work per time, which means that we can build a time derivative of the work performed, and then we will obtain the power of the system, of the machine, or whatever we are discussing. And of course, you can also formulate it the other way around. If we integrate the power over a specific time interval, we obtain the work that was performed within this time interval. If we have a constant power, this equation simplifies by simply multiplying power by the time interval, which gives the work performed. So again, let's just have a quick look at the unit. The W unit stands for watt, and 1 watt is equal to 1 joule per second. And we know joule is Newton meter, so watt is 1 Newton meter per second. An old dimension that used to be common to describe power of a system was horsepower. So 1 HP for horsepower equals 736 watt. Okay. And of course, for our forms of motion that we want to describe mathematically, translation and rotation, we can specify the power. And in case of translation, our change in work corresponds or is equal to the force acting in direction of travel multiplied by the change of distance. So it's still the same as before. I will state it again. Fs is the force component in direction of travel. Okay, and now if we substitute this equation into the equation for the power, we obtain P is equal to force times change in distance divided by the change in time. And this ds over dt, the time derivative of the distance, we know already is the velocity of the system, or the mass, the object moving. So in consequence, power is equal to force in direction of travel multiplied by its velocity. Then in case of rotation, it's quite similar. We already know that work in case of rotation can be computed by the moment causing the rotation multiplied by the angle. And again, we can substitute this in the equation, in the general equation for the power, and we obtain m d phi over dt. And the time derivative of the angle is equal to the angular velocity. Okay, and then power in case of a planar rotation is equal to the moment causing the rotation multiplied by the angular velocity. Now, in gear manufacturing, this equation has to be applied a lot. And there exists a rule of thumb to quickly compute the power that is used in different types of gears. So this rule of thumb is the following. In the last equation, that's omega, angular velocity, share from second class on. The moment m, or the v, the velocity in case of translation, and angular velocity. And the capital M is the moment. Okay. So the rule of thumb, how does it look like? The power is equal to 1 over 9,550 m times n. So n is our rotational frequency. Rounds per minute, omega over 2 pi. Dimension is round per minute. The capital M is our moment, our torque being applied. Dimension is Newton meter. And if we substitute rotational frequency in rounds per minute and the moment in Newton per meter, then we obtain the power of the gear in kilowatt. Okay, that's the rule of thumb. So now let's have a look at where this rule comes from. And this results from the equation above, the equation in the orange box. I'll state it again, m times omega. It's a result of this equation. Omega, we know that omega is equal to 2 pi n. Oops, sorry. We know that omega is equal to 2 pi m. Now, our dimension is Newton meter per minute. Now, Newton meter per minute is not yet watt, of course. So we have to convert minute into seconds. And if we do that, it's m times n 2 pi over 60. now we have Newton meter per second, which is equal to watt. Now 2 pi over 60 is equal to 0.1047. But now we want to obtain the dimension kilowatts. And for this, we have to divide by 1000, convert watt into kilowatt. Okay. So then we have 0.301047. And now our dimension is kilowatt. And now we are nearly there. Of course, it does not yet look like our rule of thumb. There's this 1 over 9,550. Here, this equation is difficult to memorize. So what they did is they converted this value of 0.0001, etc., and stated the equation like this. So 1 over this long or very small value is equal to 9,549.57. And then we end up to the rule of thumb by rounding this value to 9,550. Okay, so that's where this equation comes from, how it was obtained. Okay, that's how we obtain the power in case of translation or in case of rotation. This is kilowatt, yes. I haven't changed the dimension, so this is still kilowatt as stated here. Okay, once we know the power that is system, we can compute the efficiency of the system. And this is stated on the next page. So for the efficiency as a dimensionless parameter, eta, and it's the relation between the output and the input. So in case of the power, it's we compare the usable power to the applied power. Extracted, the power that is needed to cause the rotation or the motion, and added is the applied power, the input power. Okay, so eta, our efficiency, is always smaller than 1. There was a question?
Yeah, Miss, like I have a question from previous 2 equations. Like in those, like the velocity and the rotational velocity, the angular velocity, like both are at the equilibrium stage, or like at the terminal velocity maximum. Like if a car is going at the top speed and the air friction is the highest, is it at that the velocity is at that stage, or is it something different?
It's you mean for the computation of the power, the velocity is the current velocity of the system, which may change over time, of course. But for this time interval that we are considering to compute the power, we have to take the velocity of our object, our car, or whatever it is, the absolute velocity in direction of travel. So if it's a translational motion, then it would be the v velocity, and if it would be a rotational motion, then it would be omega, the angular velocity.
So in a case, if a body is falling from a height, like let's say if there's some air resistance, we should take the force as the air resistance and the velocity as the object's velocity, right?
Well, yeah, there would be gravity as well, of course, and then the velocity of the stone or whatever is the falling object.
Okay, thank you.
Okay. Okay, so the efficiency is, well, it could be 100, but of course, well, would be the maximum value. You can never extract more than you add to the system. But of course, in reality, the efficiency is always smaller than 1, less than 100%. Now, in case that we have a constant power, constant over time, meaning that work performed is equal to P times T, we can compute the average efficiency by using the work instead of the power. So we can also say that the efficiency can be obtained by dividing the extracted work over the added work. That's also possible. Okay, and of course, in case in a steady state motion, meaning that the energies doesn't change over time, then we could also state that the added work minus the work due to friction is equal to the work added, or the other way around, the extracted work is equal to extracted work plus work due to friction. Of course, only true in steady state, meaning that the energies stay constant, potential, kinetic, and spring energy. The components of the energy can change, velocity can increase, potential energy decrease at the same time, but the sum of all these components stay constant. Work due to friction is WR. Okay, and of course, we could have several power units connected in a serial connection. Then we could compute the total efficiency then, for example, with one power unit with an efficiency eta 1, we apply the work P1, then the power, sorry, then we extract power P2, which we use to drive a second power unit. And so on. Okay, now let's assume that this is our system consisting of 3 power units in serial connection. Then the total efficiency is equal to the extracted power P4 at the end, the final power that can be extracted, divided by the input power. And if we know the efficiencies of every individual power unit, we can compute the total power unit, the total efficiency by multiplying the individual efficiencies. So it's still the same equation as before. I simply extended it by 1, multiplying by P3 over P3 and P2 over P2. So I haven't changed the equation. But now I can replace the components by the individual efficiencies. Sorry, eta 1, of course. Okay, let's have a look at an example. We'll start with exercise 315. So just a second, I have to copy it into the script. Okay, there it is. So what do we have? We have a machine, a cutting machine with a given cutting force of 5 kilonewton, and then the workpiece has a diameter of 40 millimeter, and the workpiece rotates with a given rotational frequency of 480 rounds per minute. And we have to find the total efficiency of the lathe when the driving motor emits a power of 6.4 kilowatt. Okay, we have the force given in direction of the motion. So that's the force that we can use directly. And we know that our efficiency can be computed by dividing the extracted power over the added power. In our specific situation, the added power is equal to the power of the motor, and the extracted power results from the situation, the rotation of the workpiece and the force measured. So we added as the power of the motor. So now, what is P extracted? We have two possibilities to compute the power extracted, either using the equation for the translational or the rotational motion. Of course, in this case, our workpiece performs a rotational motion, meaning that the power extracted has to be computed using the moment multiplied by the angular velocity. Since we already have the force given perpendicular to the axis of rotation, the moment can be computed by force times radius. Radius is equal to half the diameter. And the angular velocity, just stated the equation in the script, is equal to 2 pi n. Now the 2 cancels with the 1/2, which results to F component times D times P times N. So now we have to make sure to use the correct dimension of the individual components. So it probably helps if you enter the or state the values before putting them in the calculator. Then we have the diameter, which is 40 millimeter, so 0.04 meter pi, and the rotational frequency with 480 per minute, which we have to convert to seconds. Now we have Newton meter per second, which is watt. And now if we use the calculator, we will obtain about 5,030 watt, which is equal to 5.03 kilowatt. Now we substitute this power into the equation for the efficiency. So it's 5.03 kilowatt over 6.4 kilowatt, which is equal to 0.785, 87.5%. Okay. So that's quite a simple example, of course, to start with. The relevant values are all given. We simply have to insert them into the correct equation and find the efficiency of the machine. Now, let's have a look at the second example, exercise 314. Okay. So that is our second example. In this case, we have a person on a bike riding uphill, and the person reaches a power of 150 watt on an incline with 5%. And the mass of person and bike is given by 90 kilogram. The efficiency is given with 0.95. The air drag coefficient is also given. And the coefficient of rolling or friction is given as well. We assume that the static friction between the back wheel and the ground is sufficient to transmit the necessary driving force. So meaning that there's no slipping or sliding of the tire. And we have to find the velocity that the person reaches. Okay, how do we have to approach this kind of problem? first of all, we will draw a free body diagram, including the loads of the system. So assume this incline. Then we have this bike. Oops, I like this more or less. I will not draw the cyclist because I'm not that good at drawing, but let's assume that the center of gravity, maybe here somewhere. I'll just add the force right now. So let's assume there's a person on a bike, and we know the mass of the entire system, person and bike, and then we have force of gravity m times g. Then the person moves upwards, of course, forward of the bike. Then we have a normal normal force on front and back wheel. NB for back wheel, NF for front wheel. We have static friction between tire and road. Then we have to consider air resistance. Parallel to the surface and opposite to the direction of travel. Here is called FL. I call it FL as well. And we have a driving force, and the driving force acts on the back wheel since the chain is connected to the back wheel. Okay. Now, this is our system that we have to solve. We know that the velocity is constant. It's stated in the problem description, the very first sentence. In consequence, there's no acceleration. Then we have the air resistance force. We only know the air drag coefficient. We do not know the velocity yet. So it's given by VL is equal to K times V square. Then for the friction, in case of static friction, we know that on the front wheel, that's mu R times normal force, and of course, same for the back wheel, since we have static friction there as well.
Sorry, Professor.
Yes.
Quick question.
Mm-hmm.
Normal force, it will be divided on two. I mean, the normal force will be equated to the mg, and it will be equally spread between two wheels, right?
Yes, but normal force on the front wheel and back wheel might not be of same size. They are only of same size when the center of gravity is exactly in the middle. between
Okay.
normal and between back and front wheel.
Okay, thank you.
Okay. So what else? We can build the sum of all forces parallel to the surface and perpendicular to the surface. And for this, we have to decompose the force of gravity. Now, if this is our angle beta of the incline, then we find beta here. Oh, sorry. We find beta here as well. And then we decompose.
Professor?
Yes?
The angle beta isn't approximately 0 degrees? Because cos
no.
beta is approximately 1.
Cosine of beta is approximately 1, and sine and tangents of beta are 0.05. So, but 1 is not 0.
So no, it's approximately 0 degrees, a value of cos beta, right?
Yes, because it's only an incline of 5%.
Okay.
You can simply compute the angle.
All right. Thank you.
Okay. Yep. So it's a really, it's not a very steep incline, of course. Okay. Now let's build the equilibrium conditions. So first, in direction of the normal forces, then we have 0 is equal to normal force on the back wheel, normal force on the front wheel, minus the component of gravity, cosine beta.
Professor?
Yes?
Quick question. Could you please name the mathematical rule to which this beta on the incline is equivalent to the one on the bicycle between mg and the normal?
You mean how to find the angle?
Yes. I mean, is there a name for the rule or?
No, not that I know of. It's not really a rule. It's just by let's draw the vectors. Okay, so this is our incline. This is our force of gravity acting that way, and now this force of gravity is perpendicular to the side, and we decompose our force of gravity into two components: one horizontal and one parallel, and one perpendicular to our incline. Now, if this vector mg is perpendicular to the horizontal, and this vector is perpendicular to the incline, then if you consider these two sides where the angle is in between these two sides, and you rotate the system by 90 degrees, you end up by these two vectors. And then beta is in between these two vectors as well. So you simply have to find the lines that are perpendicular to the lines defining the angle beta. And then if you have these two lines, the angle beta is in between these two lines as well. Of course, they both are perpendicular.
All right. Thank you.
Yep. Okay. So as given in the problem description, the cosine of beta can be assumed to be 1. Then we have mg is equal to nb plus ns. And for the second equilibrium condition, parallel to the incline, we have 0 is equal to driving force minus the force of friction on back and front wheel, minus air resistance, and minus the component of gravity, sine beta. And again, as given in the problem description, sine beta is equal to 0.05. 5% incline.
Professor,
Yes.
I'm sorry. Isn't the bike moving? How can we use the static equation with 0?
No, it's not a static equation. It's a dynamic equilibrium condition. So remember, in statics, we said that our system is at equilibrium as long as it's not moving, or as long as it's when it's moving with constant velocity rectilinearly. And this is the case for the bike here. It's moving with constant velocity rectilinear. It doesn't make any turns. It doesn't accelerate. And this is also a static system.
Yes, I forgot about this. Thank you.
Yeah, you're welcome. Of course. Okay, now let's rearrange the two equations that we obtained. And first of all, we have these equations right here. The equations, the relation between normal force and force of friction. Then we can substitute the equation. I'll just number all the equations in equation number 3. So 1 and 2 goes in 3. Then we obtain m times g is equal to mu r, not mu r, but 1 over mu r RB plus RF. Okay, and now we use this equation and put this into equation number 4. Can rearrange it first, maybe helps you see what we do by multiplying with the friction coefficient like this. Okay, now let's call this equation number 5. And now we substitute equation number 5 in equation number 4. And at the same time, I will rearrange equation number 4, putting the driving force on one side and all other components on the other side of the equation. Okay, so we have F is equal to then the two forces of friction, which are equal to mu r mg, then plus mg plus and FL is equal to kV squared. Sorry, I missed the 0.05. Okay, mu r is given with 0.01. And then we obtain 0.06 mg plus k v squared. Okay, now we want to solve for the velocity, but we do not know the driving force. So what can we do? What else is given? What we also know and haven't used yet is the power of the driver, which is an added power, the power the driver adds to the system, and the efficiency is also given. Now, this indicates that we have to use the equation for the efficiency, and that's what we will do next. So again, first I will state the general equation. The efficiency is given by power extracted over the power added. The power added is the power of the driver. We'll just have a quick look how it's named in the problem description. Simply P. Okay. Okay, then the work extracted in case of a translational motion. Oh, wait, there's Well, in this case, it wouldn't make any difference. But of course, if we have an object with two contact points, then there are two normal forces and two forces of friction. That's the real situation. If there are no dimensions given and we are not using the equilibrium of moments, then we could simplify it to one normal force and one force of friction as well. So this would work in this case here, but of course, the exact approach would be applying a normal force to every wheel, since both wheels are touching the ground and exerting a normal force to the surface, to the ground. You know whether the power is added or extracted from the problem description, because here it says which velocity reaches a cyclist with a power of 150 watt on an incline, etc. So the cyclist has a power or applies a power of 150 watt. The power is not being extracted from the system. There's then you know what it is. So it depends on your situation. Is it put into the system from a person in this case, or from a motor in the previous situation? Then it's added power. And then the extracted power is the power needed to perform the motion. Yeah, with a certain loss, of course. Okay, so power extracted. In the script, we just discussed that the power extracted in case of a translation in motion with constant velocity, the power is equal to the force in direction of travel multiplied by the velocity. And the force that is our driving force, the force causing the motion, force component in direction of travel. So it's the force, the equation above, multiplied by the velocity, and then it's divided by the power of the person, the cyclist. Okay, now we can substitute the force. So we have 0.06 mg times velocity plus k v, or velocity, to the power of 3. Divided by power added. Okay, now let's rearrange the equation. Then we have eta times p, efficiency times power, is equal to 0.06 mg times velocity plus k times velocity to the power of 3. Okay, now I will substitute all the values given. The efficiency is given with 0.95, the power is given with 150 watt. Then we obtain 142.5 watt. Mass is given with 90 kilogram, and the g, acceleration of gravity, is given with 10, or will be assumed as 10. Then we have 53 Newton times velocity, and k, the air drag coefficient, is given with 0.25 Newton square second over square meter multiplied by the velocity, the power of 3. Now, we do have obtained an equation with only one unknown. But of course, this equation contains the unknown itself, and the unknown multiplied by the power of 3. You're right. I used for if you use 10 for G, then it's 54, and in case of 9.81, it's 53. That's correct. Okay, so we cannot directly solve this equation. So what we have to do is we have to integrate to obtain a solution. So we can integrate by hand in this simple case for this still quite simple equation. And this works as follows. First of all, we have to make an assumption. And now I would assume that the person, that the second component of the equation is much smaller than the first part of the equation. So I will rearrange the equation, and then it will become clearer. We can state this equation like this. Oh, sorry, by other way around, of course. Now we have the value 53 or 54, the first part of the equation, and 0.25 times the square of the velocity. Now I would assume that the second part, this part right here, is much smaller than the previous part of the equation, because the velocity will not be that high, and we have to multiply by 0.25, like dividing by 4. So it's very likely that it will be smaller. So that's the assumption I make. Of course, it could be wrong. We will figure out if it was correct or not at the end. So I assume that KB squared is smaller than the 53 Newton. Then if this assumption is true, then the then we can rearrange, or we rearrange the equation right in front for the velocity by stating that the velocity is equal to 142.5 watt over, and I'm not neglecting this component, okay? But now, with this assumption, I can apply an estimated value, v tilde, to this equation, and then I can compute the velocity on the left-hand side of the equation. And when my assumption equals the final velocity, my value will be correct. I will have obtained the absolute velocity. Of course, this will not be the case for my first assumption, because I have no idea where the velocity, in which range the velocity might be. Then I make an assumption, and I will obtain a velocity which does not match my assumption. But then I will use the computed velocity as my new assumption and compute a second velocity, and so on. And that's a iterational process. And I can do this as long or until I reached my a velocity that is exact enough for my comparing to my assumption made. Okay, before we start the integration, we will check the dimensions first to make sure that we rearrange the equations correctly. We have watt, which is equal to Newton meter per second. And we have Newton plus Newton square second over square meter, and v square is meter square per second square. Then the seconds cancel, the meter cancels, and then we have Newton meter per second over Newton plus Newton is Newton. Then Newton cancels as well. And our dimension is meter per second, which is the correct dimension for velocity. So this equation, at least, is correct. Now, let's start the iteration. Now, first step, I assume that the velocity is 0. Of course, that's not true, but if you iterate to obtain a solution and you have no idea where your solution might be, which size it might be, then it's usually a good idea to start with 0. That's what numerical programs do as well. If you do not define a starting value, then it will start with 0 as the first guess. Then we insert this velocity in the equation above, and we obtain a velocity of 2.69 meter per second. So as expected, they don't match. So we have to perform a second step in our iteration, assuming that our starting value is equal to the computed value, 2.69 meter per second. And now we already obtain a velocity of 2.60 meter per second. So we get closer quite quickly. Let's say that we want to have an exact value until the or third digit, okay? So right now we are exact until the first. Our starting velocity has to match the final velocity. So v tilde has to be equal to the velocity itself. When this is true, our equation will be true. Okay, if our this is our starting value where we assume a velocity, and if our assumption is correct, we will obtain the same value here because it's the same velocity. They result from the same equation. We simply rearrange the equation. And now we use our guess to obtain the correct value. And if we keep doing this for several steps, we will obtain the correct solution. Okay. Now, third step, we apply 2.60 meter per second, and we obtain 2.606. Meter per second. So getting closer. The second digit is correct. Now for the fourth step, we apply 2.606, and we obtain 2.605. If you get fourth digit, it's 2.6052. So now we are almost there. Through a fifth step, v tilde is equal to 2.6052 meter per second. Then we obtain a velocity of 2.6052 meter per second. And that's good enough for our computations. Then the velocity of the bike is 2.605 meter per second, which is equal to 9.4 kilometers per hour. Usually, well, it depends on the size of the velocity. If we are talking about like 10 meter per second or 100 meter per second, then 2 digits would be enough. If it's a small value, just one number before the point, then maybe 2 or 3 digits. But that would be enough. Okay. If we're talking about 100 or 200 meter per second, then maybe even 1 digit would be sufficient. And for the previous question, the efficiency is given for the entire system, not just for the gears. It's given for the gears, but there's no other loss in the system.
So in the efficiency that we have been given, the friction force have been considered, right?
Yeah, well, we considered the force of friction in our equations. So we did consider the friction and the air resistance as well.
Of course, but what I mean is that it's not considered twice. So the efficiency that is given, it has already considered the friction force, right?
Exactly. Otherwise, we would double the effect.
Of course, in a more realistic system, for example, the bike would change its roads from like an inclined plane to a straight road or something like that, and friction forces may change with that, or like the coefficient of friction of the roads, things like that. The efficiency is not a stable number, right? I mean, it changes with the different conditions.
It depends on the situation, yes. But then if it changes, then there should be information about it, okay? And but in this case, it's only one situation, a given incline, a given power, given friction coefficient, etc.
Okay, okay, Professor.
Okay. Well, in this case, there is no simpler way to obtain the solution. So you would have to integrate. But usually, the most problems given do not require iterative process. So if we, for example, if we neglect air resistance, that would be quite simple to solve, because then this component with the V square vanishes. Then it would be simple, okay? So we will solve other problems where we will obtain the solution without performing any iteration. Okay. If there are no more questions, then I would like to return to the script, because as I told you at the beginning, chapter 3 is a short chapter, simply introducing basic values, power, efficiency, work, energy, and these kind of things. And now we will come back to our motions and apply this knowledge from chapter 3 to the different types of motion. As in chapter 1 and 2, we will distinguish between point masses and rigid objects. and we will distinguish between translational and rotational motion, referring to leading and relative motion, or translation and rotation to obtain the absolute general motion. Well, we didn't neglect it here as well, but it always depends on the situation, how big the effect of air resistance is. I don't think you did a lot of physics examples with air resistance. You probably neglected in most cases without even talking about it. Okay, so next chapter, chapter 4. And of course, we will start with the simple case, the point kinetics. And as we already discussed in chapter 1, it's valid for point masses, meaning a mass without any spatial dimensions, or when we describe the center of gravity of a motion, only the center of the gravity, and we concentrate all the mass in the center of gravity, or third situation, if we consider translation of bodies. As long as there's no rotation of an object with spatial dimension, that can be described using the point kinetics approach as well. Now, we use Newton's second law, and Newton's second law says that the change, that the force applied to a system causes the change in motion. And that's the equation right here. Mass times velocity is the impulse. That's what Newton said. And building the time derivative of this corresponds to the forces in direction of travel. And of course, in general, if the mass changes over time, the time derivative would result into two components: mass over time derivative of the mass multiplied by the velocity, plus the mass itself multiplied by the time derivative of the velocity, which is equal to the acceleration. Okay, in case of a constant mass, we this equation simplifies to the equation in the second box. Change of mass occurs, for example, if we describe a car and we consider the gas loss during the driving, something like that. Okay, for obtaining the solution, we apply the principle of D'Alembert. And what this means, is what we will discuss in the next few minutes. In case of a point mass that performs a general motion, the obtaining the solution, meaning describing the forces, describing the loads acting on the system and causing the motion, this approach is quite similar to what you learned in Engineering Mechanics 1. So first thing we do is we have to free the components of interest. Then we have to mark all loads, external loads, and the support reactions. And this is new compared to Engineering Mechanics 1. We have to mark the additional internal inertial force. And this inertial force acts in the center of gravity, if it's an object with spatial dimensions, or in a point mass, of course. And this inertial force acts opposite to the direction of the acceleration, because it's inertia against the change in motion. An acceleration changes the motion of the object, changes the velocity of the object, changes the direction of the motion, and the object, the mass itself, has an inertia acting against the change of motion. And that's what's stated right here. So if we add this additional force, we can build the dynamic equilibrium equation, which are, from the procedure here, the identical to Engineering Mechanics 1. Sum of all forces in horizontal and vertical direction. And if it's a three-dimensional object, we could build the an object with spatial dimensions. We could also apply the equilibrium of all moments. So, for example, in Cartesian coordinates, in case of a point mass or a pure translational motion, it would result in the following equations. Oops. Okay, like this. So in statics, you will only have the sum of all forces is equal to 0. And in dynamics, we have to add the inertial force mass times acceleration, which is negative, which points opposite to the direction of the acceleration. Now, as I already said, if we have a body, an object with spatial dimensions performing a pure rotational motion, we can also build the equilibrium of moments, which is identical to engineering mechanics 1. So it would be so, but this is only true in case of translational motion. I'll just go back in a second. So with respect to any arbitrary axis with an inertial force. I'll just go back to the previous page and then come back here. Ft, that's our inertial force, m times a. Here.
And Fi, Professor, can you repeat that?
That's the sum of all forces. Sum over I. So if we have like two forces acting on a system, then it would be force 1 plus force 2, etc. As in statics. I think you should know this part from statics.
Yeah.
Yeah. Okay.
So if a system is moving and forces are acting upon it, it's as if it was static and plus the max.
If the system
MA,
was,
sorry.
if it would be a static system, is that what you asked?
No, what I'm asking is that, for example, we have a standing ball and a rolling ball, and forces are acting upon both of them. The only difference is that the rolling ball has an MA.
Yes, exactly. Well, of course, only if you consider the ball being a point mass.
Yeah, of course.
Yeah. Okay.
Thank you, Professor.
Yeah. Okay. Yeah, that's correct. Okay. Let's go back here. So, special cases. There are 3 special cases that simplify the equations, the previous equations that we just discussed. So first one is a rectilinear motion of a point mass or a linear translation of a body. Of course, in this case, our acceleration would be 0 in 2 directions, and there would only be an acceleration in 1 direction. For example, in the x direction. Could be another y direction or z direction as well, of course. But in this case, there would be only 1 acceleration. And of course, in case of a translation, there are no angular components, angular velocity or angular acceleration. Then if we have a circular motion of a point mass or a circular translation of a body, then, so a pure circular motion, then there would only be a tangential and a normal component of the acceleration, as we discussed at the very beginning of the class, page 1 in our formulary. And from this result 2 inertial forces, one pointing opposite to the tangential component and the other one pointing opposite to the normal component of the acceleration. And the third situation is the relative motion of a point mass or translational motion of an object of a body. So in case of a relative motion of a point mass, we can apply our standard approach. The absolute acceleration consists of leading and relative motion, and then there might be Coriolis acceleration that has to be considered as well. And then in the dynamic equilibrium condition, there would be 3 inertial forces. One acting opposite to the leading acceleration, the second one opposite to the relative acceleration, and the third one opposite to Coriolis acceleration.
Excuse me.
Yeah.
If in case the acceleration in the x direction in point 1 is also 0, then the normal static conditions would apply, right? Like we did in the previous question.
Yes, then it would be a static system, exactly.
Okay, thank you.
Yeah.
Sure, Professor. In the case of relative motion of point masses, the Fi has different directions. For example, we might, as the object rotates, we might have forces acting in x and y direction. And accelerations L and R are 90 degrees apart from each other. How are we going to consider the directions of the forces? Because we cannot just... Oh,
they are vectors.
Thank you.
So always keep in mind that these are vector equations. Okay. Yeah. Other questions? Okay. If not, we will spend some time in this chapter solving different exercises, different examples, and I think we'll do about 5 to 6 examples. And we still have some time, so we can start with the first one, which would be exercise 4.1. So. Okay, there it is. Okay, in this example, we have a car given with a rear wheel drive, and we have to find the maximum acceleration in case that the driving wheel just does not slip. Okay, the coefficient of static friction is given with 0.6. So be careful with the coefficient of friction. From engineering mechanics 1, you know that there's static and sliding friction. And for static friction, you have the index 0. And for sliding friction, there is no index to the friction coefficient. And here we have the friction coefficient given in case of pure rolling static friction. Air resistance and rotational inertia are negligible. And in the second part, we have to find the acceleration for which the front wheels would be lifted. So maximum acceleration without slipping is the first part, and second part, acceleration when the front wheels would be lifted from the ground. And we have values given, dimensions of the car, and that's it. Okay, so how to approach this problem? Of course, again, we will start with our free body diagram. So that's the car. Now, direction of travel is given. And the green values are our kinematic values. Red are our loads. So when building the equilibrium conditions, we are only considering the red forces, okay? So what do we have? We have gravity in force of gravity in the center of gravity, of course. Then we have a normal force on back and front wheel. Okay, and now we assume our force of friction on the back wheel, since we have back wheel drive. And now it's always a question, in which direction should it point? And of course, in statics, you learn the force of friction points opposite to the direction of motion, or to the most likely direction of motion. Now, in case of a tire, we have two types of motion. First of all, the car itself moves to the right, and when the tire rotates, the direction of rotation is to the left. Velocity and angular velocity. Now, we have two options. We could draw the force of friction opposite to the direction of the translational motion, or opposite to the rotational motion. But now we have to decide which direction we choose depending on the problem description. And in our case, in the problem description, it is stated that the car is being accelerated, and we have to find the maximum acceleration for which the driving wheel just does not slip. And in this case, slipping would be that the wheel rotates faster than the car translates, moves translational. And that's why we should draw the force of friction opposite to the direction of translation. Okay. So, of course, since it's static friction, and that's what you also learned in Engineering Mechanics 1, it wouldn't be wrong to draw the force of friction in opposite direction. But you know that in case of static friction, you have this equation between force of friction and normal force. And here you have to make sure to build the absolute value. So once you use this equation for static friction, you have to make sure that you use the correct force of friction, correct sign of the force of friction by building the absolute value. Friction force is always positive. Yes, I can repeat what I just said. So if we have a wheel, a tire, and the center of the tire, the axis of the car, moves with a given velocity, and the tire rotates in this direction. Then down here, we would have velocity due to translation pointing to the right, and velocity due to rotation pointing to the left. Now, force of friction, in general, the force of friction points opposite to the direction of travel. It acts against the change of motion, okay? But now here we have two components pointing in opposite direction. Now, we could draw the force of friction opposite to the translational component or opposite to the rotational component. We do not know the direction of the force of friction in case of static friction before solving the system. But of course, we can make an assumption, and this assumption can be good or maybe not as good. So we have to think about what is more likely to happen. So for this car, the car is being accelerated, and the acceleration takes place by applying a moment to the tire, by increasing the rotational velocity of the tire. So if the tire starts to slip, it will rotate faster than it translates. Then it will rotate, well, not on the spot, but it will rotate faster than it moves forward. For example, on an icy road, if you accelerate too fast, then your tire slips, and it slips because it rotates fast, but it has not enough grip to move forward. And in this case, we would draw the force of friction opposite to the direction of rotation. So if R omega is greater than V, or if this is more likely to happen, then this would be the direction of force of friction. In another situation, if your object or mass is more likely to translate faster than it rotates, then your force of friction should point opposite to the direction of translation. So for example, this can happen if you have a tire, or if you have a cylinder or whatever, an object, and you apply a driving force to the center of the object. If you apply this force and if you increase this force, it's more likely that slipping occurs due to a faster translational motion than a rotational motion. Okay, so that's what you have to. Yeah.
Like in the front wheel, for example.
Well, in the front wheel, there is no driving force. So the front wheel is simply, or there's no force or torque applied to the front wheel. The front wheel is free, and it simply keeps rolling with your system. So there is nothing braking or accelerating the front wheel. So we don't have to worry about the front wheel.
Excuse me, Professor.
Mm-hmm.
But in this case, the situation 2 applies, right? R omega is less than V because there is no slipping. It says it just doesn't slip. Or
it's not yet slipping, yes. But the question is, what is the maximum acceleration that it just does not slip? So it's about to slip. And as long as it's not slipping, there is the velocity here is 0, right? Static or kinematic condition. But once it slips, the kinematic condition is not true anymore.
Yes. Okay.
Okay. I will just quickly, we have to include our inertial force in the center of gravity opposite to the direction of acceleration, ma. Okay. And that's where I would like to stop now. If you have any more questions, then you can still ask. So I'm still here for a few more minutes. And apart from that, or if you don't have any more questions, then I wish you a good weekend, and we will discuss this problem and some other problems as well, of course, on Monday, and you'll have time to solve problems on your own. Chapter 4 problems. Yes.
Can you please go back to the lecture notes for 1 second? Yeah, thank you.
That's your question? Okay.
I just missed the last.
Okay, yeah, okay.
I'm really sorry, Professor, but I have a question regarding the problem that we solved on Monday. If it's convenient, when everybody if anybody has a question, maybe I will be in the very end. I have just a really quick question.
Yeah, if it's a quick question, then go ahead.
Okay, then the second problem that we derived on Monday.
Yes.
I couldn't figure out the sign of the potential energy when we were deriving the equation for the general case. I think there was a minus, and I'm not sure why did we write a minus there.
Well, because we chose the 0 level to be in the static equilibrium position. And then our situation E0 and E1 both were below the 0 level. So both of them were negative, less potential energy than in the 0 level.
Okay, because both cases were below the 0 level. Okay,
exactly.
perfect.